Welcome back. So, we were discussing of the different subsystems in the satellite bus, and we have covered AOCS, TTC, power. Briefly, we will touch upon the other subsystems. The propulsion system is already, we won't go into detail of that because some part of the propulsion system is already mentioned during the AOCS, attitude and orbit control system. So, we will talk about the thermal now. The temperature variations are large in satellite, because the one side, the face of the satellite which is facing the sun is facing large temperature, whereas the other side of the satellite which is facing the cold sky is a very low temperature. So, there is a large temperature gradient, and there is some typical numbers I have listed here for different subsystem which faces this type of variations. Your satellite is also slightly tilting all around Earth. Following are some temperature range specification for different subsystem. Some typical numbers, you can see the range. Antenna faces the maximum because it is outside. Electronics on the standby, they face larger compared to the which is in operation, because when it is in operation it generates its own heat. Then the solar power generator that is also facing large variation, battery in standby and battery in operational, similar to the electronics standby and operation, there is a variations of that. Sun sensors and propellants, these are typical numbers, and all are in degree centigrade. Now, to in vacuum, we have to remember that satellite is particularly geosynchronous satellites are in almost vacuum and no convection. There are three modes of dissipating heat, that is conduction, convection, radiation. So, only conduction and radiations are possible, and that too conduction is possible only where the metal pieces are there, through that radiation is the mainly thing. So, when there is a thermal imbalance or thermal gradient variation is very large, certain remedial measures are taken to take away the heat if the hot spots are generated at certain spaces. So, that can be done by doing certain heat exchangers, that is, you can use the thermo optical behavior of the surface, and the surface has certain facing that sun, and that part is temperature is high, use that one, and the other side is a cold sky, that temperature is low. So, use that one. So, local source of heat also can be generated by the electric heater. When it is very cold and it is going extreme very cold, you can switch on certain local heaters, and cooling can be done by exposing some part of the hot spots towards the cold space, so that radiation can take place, and there can be heat pipes, which is a metal pipe with some fluid inside, can be attached to the hot spot, and that heat pipe can carry the fluid which is inside the pipe in convection mode to the colder area. There are various techniques people use. There is thermal modeling done. Anyway, as a communication engineer, we do not have to worry much about it. So, this is about thermal, and the last part is the structure which is holding the satellite. It is the supporting onboard equipment from the shock and vibration during launch and during operation. It permits the separation and deployment of the appendages like the solar panel, like the antenna, which has to be deployed, and during that certain jerks and shocks and vibration that can occur. One thing, the structure should not be heavy. Structure itself, which is holding all the electronics and other systems, should not be heavy, and generally as a thumb rule it is taken as 5% or less than 5% or less than 5% of the total mass of the satellite. So, therefore, it is not a plain sheet of metal. You can see in the right side, we have shown two pictures, which is honeycomb type holes are there, and these are the metals outside the body. This gives strength as well as its weight is less, and these can be made of aluminum or fiber. Aluminum or magnesium alloy with honeycomb panels are used for the body, or carbon fiber which is used for the antenna part. So, the structure has to be here also. It is only information we need for communication engineer, not much is required. So, with this very briefly we have gone through the different parts of the subsystem which contains the satellite bus. So, let us go back to that old diagram of us, that is satellite bus is the platform that support the payload operation reliably throughout the mission life, and payload will be microwave repeater, mostly it is microwave repeater and the antenna, and the satellite bus is AOCS, TTC, the power, propulsion, thermal and structure. Briefly we have gone through each of them, except the propulsion we did not do much, we have taken its part of AOCS, right. So, now let us concentrate to find out what is there in this payload. Okay. A communication payload, what is that? A communication payload, we were using from the beginning the term, it is a microwave repeater. Its main function then should be to receive, the amplify and transmit the signal to the earth, out towards the service area. It receives the signal from the service area, amplify the signal and transmit it back. That is what is the payload. But let us see the complexity which lies inside it. Signals at the input of the satellite is extremely weak due to the loss in the free space, because there is a long distance in the orbit from the ground when it is going. The power is becoming very weak. Let us do some rough calculation, very rough. Do not take it as a very correct or pure calculation, just rough, some numbers we will put. You have seen that ATMs, bank ATMs, and near the ATM, either top rooftop or somewhere nearby, you will find a small antenna which is looking towards the south, and that is called very small aperture terminal, VSAT. We will try to learn about VSAT later when we talk about the ground system. Right now, let us see a typical signal level received at the satellite from your VSAT, the bank ATM. Just let us take some numbers. VSAT transmit power is 43 dBW, and the range from the VSAT to the satellite is 40,000 kilometer. And satellite receive antenna, the effective aperture through the size of the antenna diameter, so that it receives, that aperture area is 0.098 meter square, some typical numbers for calculation. So, the receive power is the power flux density multiplied by the receive antenna effective aperture, the transmit power by the 4 pi r square, that will make it power flux density into the receive antenna aperture. And if we put the numbers there in dB scale, the transmit power minus transmit power in dB minus 10 log 4 pi r square, r is the distance, that is the range 40,000 kilometer, plus 10 log 0.098, and it comes out to be minus 130 dBW, because 43 dBW was their transmit power, in dBm minus 100 dBm. I mean, in terms of watt, this dBW if you put in terms of ratio, then it comes 1 into 10 to the power minus 13 watt. You just see 10 to the power minus 13 watt is the level of signal even when you are transmitting 43 dBW. You can find out in ratio what is the 43 dBW means, in how many watts it is. So, therefore, it is a very small signal that is received. Let us go back to the diagram. So, there is a small amount of signal which is received. Let us assume that after the antenna it has come, that is minus 130 dBW, and to make it 0 dBW, which is equivalent to 1 watt, I have to put a lot of amplifiers. So, instead of one amplifier, I put more blocks of amplifiers, and then there is transmit. So, overall amplification I want to give roughly about 130 dB. It is quite large number. So, there is a possibility, if there is any leakage this amplifiers, the whole system will start oscillating. With this high gain, there is a high possibility of the instability of the receiver. So, there has to be certain isolation, sufficient isolation needed between the receiver and transmitter. Now, this nominal figure of the isolation should be more than 40 dB and over the gain. So, 130 plus 40, 170 dB is the total isolation required. It is a very large number. So, various techniques are used. This isolation is achieved through the frequency separation between the transmitter and receiver. So, whatever transmitter frequency we are transmitting and whatever frequency we are receiving, they are separated out. That means it is not only amplifier, we have to convert the frequency to another frequency. Then you do a lot of filtering, of course, and then we do RF shielding, so that the transmitter power, which is much higher compared to the receiver input signal, which is very low. So, a lot of shielding is done. Also sometimes we do the polarization orthogonalization transmitter. Polarization part we will discuss during the antenna discussion. Now, let us look at the spectrum which is allotted by ITU. We have seen in the earlier slides. I have roughly shown here as C band is almost 6 gigahertz, that is 5.9 gigahertz to 6.7 gigahertz is earth to space, and space to earth is allotted 3.4 gigahertz to 4.2 gigahertz. In terms of megahertz it is listed here. So, that is International Telecommunication Union specification. They have specified that KU band also, which is 13.8 gigahertz to 14.8 gigahertz in the uplink, which is earth to space, and 10.7 to 11.7 gigahertz in the downlink, which is space to earth. At Ka band, another chunk is 2.7 gigahertz to 27.5 gigahertz to 29.5 gigahertz, and 17.7 gigahertz to 19.7 gigahertz. You can see that at C band we have a bandwidth of much lower compared to the KU band. KU band you have almost 1 gigahertz bandwidth, Ka band you have almost 2 gigahertz bandwidth allotted. It is not a contiguous band, you can see the regulation in that, but this is the rough. Certain things from this table, look at it very carefully. Do you see that the uplink frequencies are always higher than downlink frequency? So, why uplink frequency and downlink frequencies are widely separated? One is that question, and that is why the downlink frequency is lower than the uplink frequency. You should find out the answer from the books. Okay, this is very interesting to know. Okay, let us go back to the payload. So, we have minus 130 dBW. Obviously, we have to put a lot of filters, amplifiers, and we have to change the frequency. So, we have to have mixer, and downlink frequency is lower. So, which is F2 is lower than F1. So, it is down converted, again filter, again amplifier, and we put. So, you can see a lot of filters coming. So, each of them can be put into different subsystems. The functions of the repeater now, let us put definition and then we will go to the subsystem. One is the receive the signal from the service area. So, you need a receive antenna. Then amplify only the required receive band. You might be receiving many things based on the antenna capacity. It is receiving many signals. Out of that, only the required band has to be taken. So, there has to be certain filter, and since the signal is very weak, you need low noise amplifier. Then convert that to a downlink band. So, there has to be a mixer, local oscillator, and filters and amplifiers also, and then amplify and remove the spurious, that is powered amplifier and filter, and then transmit to the service area, that is the transmit F2 into through the transmit antenna. So, these are the basic functions of that. Let us see each of these. Most of the circuits are nonlinear. One thing you have to see it very carefully. Now, general model of nonlinearity can be seen by a Taylor series like V0 and any nonlinear polynomial. V0 is equal to A0 plus A1 VI, A2 square, or A2 VI square, or A2 square, A3 cube VI cube, etc. So, if VO is the output, that is the resultant voltage, depends on the input voltage square, input voltage cube, Vi square, Vi cube, and multiplied by certain coefficients. Now, if the inputs are two frequencies, like Vi is V0 cos omega 1 t plus cos omega 2 t, possible because many people are communicating with this satellite. So, at least minimum 2 should be there. So, two frequencies omega 1 and omega 2 are communicating. Then replace in this Taylor series wherever Vi is there, Vi square, Vi cube, replace into V0 cos omega 1 t plus V0 cos omega 2 t. I have taken both the signals are of the same amplitude V0. They may not be same. For simplicity we have taken this. Then you will find that there are many frequency components that arises. One is of course the DC, the A0 part, then the omega 1, omega 2, two fundamental parts, then omega 2 minus omega 1, omega 1 minus omega 1 plus omega 2, 2 omega 1, 2 omega 2, 2 omega 2 minus omega 1, 2 omega 1 minus omega 2, like that will continue. So, many frequencies are generated through this nonlinearity. There are certain advantages and disadvantages. Let us see the advantages and try to find out. So, if there are two frequencies omega 1 and omega 2 in the frequency plot, if we do, near DC something will be generated, omega 2 minus omega 1 will be generated very near to DC, then 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1 generated near to omega 1 and omega 2, that is two fundamentals. 2 omega 1 and 2 omega 2 will be generated far away, and then there will be two only omega 1 plus omega 2, another carrier. So, like that many, I can say, spurious signals are generated. Omega 2 minus omega 1 can be used for down conversion, the input frequency and local oscillator frequency can be used. Omega 2 plus omega 1 can be used for up conversion. N times omega I, let us say omega 1 or omega 2, that is 2 omega 1 or 2 omega 2 or 3 omega 1, 3 omega 2, this can be used for frequency multiplication. 2 omega 2 minus omega 1 is a spurious intermodulation product which can appear very near to the fundamentals. There may be many other intermodulation products. So, like that each of them, each of the frequency component has certain use. So, we will try to use them. Let us go back. So, we have after the antenna input band pass filter, it rejects the out of band signals, that includes the transmission from the same satellite and adjacent satellite and any out of band signal received from the service area. From the same satellite it can come because spurious are generated that can be fed back from the transmitted receiver. Adjacent satellite might be using some of the signals which are out of band, is received by the antenna. Out of band signal from the service area somebody else is transmitting, which is coming as interference. All these things have a filter out, which are out of band. And typical bandwidth of C band is about 500 megahertz, 500 to 700 megahertz based on the allotment. And so, the input filters are of that size. In Ku band, Ka band, it may be of different bandwidth. Then there is a amplifier which is LNA. So, input signal is very small, very low, very weak. So, the first amplifier generally about 100 times gain is given, that is 20 dB gain, which is a very weak signal, and then it should not add much of a noise. So, it is low noise. We will discuss about the noise much later. So, that is why it is called low noise amplifier. The first amplifier has to be low noise amplifier, but it is giving smaller gain. So, we have to put additional gains, that is more gain of the order of 30 dB or more are provided for subsequently amplified stages to the input requirement of the down converter. There will be down converter after this. So, input requirement of the down converter needs certain level, therefore, you have to put more amplifiers, and typical specifications for these amplifiers are noise figure. We will discuss that one later. Receiver sensitivity, that is minimum detectable signal level at the input, the gain and the dynamic range. There are many more specifications, but these are certain important specifications of this LNA and subsequent RF amplifiers. After that, we come across the down converter and local oscillator, which is a part of the down conversion. Local oscillator, mixer and filter. It is a nonlinear device which mixes the input signal with locally generated signal to produce required downlink frequency. We have seen omega 2 minus omega 1, and then to reduce unwanted harmonics, a band pass filter has to be put after the mixer, and in some cases down conversion is to another IF instead of directly to the transmit frequency, another IF at lower frequency is done, and then signal is up converted, is called double conversion type repeater. You are aware of this type of thing in your BTech classes, you have seen. Local oscillator is generally good stable oscillator. So, it is at much lower frequency 10 to 100 megahertz, and then it is multiplied, that n omega 1 nonlinearity is used. This is multiplied and amplified to generate the required LO frequency, that is local oscillator frequency for mixing. Stability is important, it is roughly of the order of 1 in 10 to the power 6, which is 1 parts per million. Here I ask you a question, there is a band for INSAT satellite. The uplink band is 5.625 gigahertz to 6.425 gigahertz a band, and downlink band is 3.4 gigahertz to 4.2 gigahertz. It's a band. What will be the INSAT LO frequency, which converts the whole bunch of the input signal converted to the output signal, which is downlink? Now let us go back. This you have to solve the problem. You have to find out. It is very simple. Now important parameters for the local oscillator are the stability and the oscillator phase noise, which is nothing but a short term random fluctuation in frequency or phase. Now we have to see the total frequency band. In C band we said 500 megahertz, that needs to be segmented. There is a need for it. Generally the output amplifier, power amplifier, covers the complete band. It is a wideband amplifier, but the gain provided is relatively low, and of course you have to give maximum power, so you have to drive it to the maximum near saturation, so it is nonlinear. So therefore many spurious will be generated. So for large number of carriers, as input carriers means the different users which they are sending signals, each carrier get only small share of the total power given by the amplifier, and the large number of intermodulation products also will be generated, which will act as a noise. So therefore these two problems of lowering getting individual carrier as lower power as well as getting more noise, if you take in each amplifier small number of carriers and then sum them up later, that could be one solution. In that case, each carrier in each of the amplifier will be having much larger power. So the band is then divided into several sub bands, which you call channel. Each is provided with a separate power amplifier, and then all signals are combined. This part of the subband generation and signal handling is called transponder. This is a terminology we were using from the beginning, so here it is coming. So once you try to separate a segment, you need separate filters. So Subman formation is done by a demultiplexer, which is nothing but band pass filter, bank of band pass filter. These filters should have high adjacent channel rejection because they are contiguous, and low amplitude and phase ripple. Filter phase and amplitude ripple should be low over the pass band. So the whole frequency band which is available is now here I have shown, each is divided by 40 megahertz segment, and since the filter characteristics are gradually increasing and then steady and then decreasing, so therefore the steady part is taken roughly as 36 megahertz, the constant amplitude. So the transponders are, each of them are 36 megahertz wide, roughly. Generally that is the standard, I should not say standardization, generally is accepted by industry. And then the power amplifier, when power requirement is more than 20 watt, TWT amplifiers are used as high power amplifier. HPA is high power amplifier. TWTs have lot of nonlinearity, and so there has to be linearizers that are used. We will discuss that one much later, what is the nonlinearity, what is their effect, but this linearizer increases the complexity, weight and cost, etc. And solid state power amplifiers are used when the power is less than 20 watt. These are all typical numbers. There may be 40 watt solid state amplifier available nowadays. SSPS is less efficient compared to the TWTA, that is conversion efficiency from DC to RF, but it needs less space and weight and lower voltage operation. So for lower power operation, SSPAs are preferred nowadays. Critical specification from the power amplifier are input power for output saturation, how much input power will give the output saturation, that is defining the nonlinearity or 1 dB compression, gain variation, the 1 dB compression point, third order intercept point, amplitude modulation to phase modulation, AM to PM conversion, these are also part of nonlinearity. We will discuss those things later. DC to RF efficiency, conversion efficiency. Then each of these amplifiers output has to be combined again, so we call another multiplexer, which is output multiplexer. All HP outputs are combined through another bank of band pass filter. This is called output multiplexer. These band pass filters are difficult to design because it has to handle high power, because already power amplifier has been put. this is a high power and low loss filter, and output mux or O mux is connected to the transmit antenna. So, a transponder consists of input mux, the power amplifier, and output mux, and the overall specification of the transponder is channel bandwidth, adjacent channel rejection, group delay, and I can draw the picture now is the uplink frequency which is coming as a receive antenna, and then the receiver is nothing but the input filter, and then low noise amplifier, and then down converter. Of course, there is a filter here, and after the down converter, that the input mux, which is demuxing actually taking place, and then amplifiers. I have shown one amplifier, and then output mux, which is combined called transponder, and then the transmit antenna, which is going as a downlink. Now, we can do some quick power estimate. DC power to RF power is by the efficiency, DC power multiplied by the efficiency, or RF power divided by the efficiency is DC power. Now, for when there are many transponders RF TRP, then it is a sum of RF TRP is the total DC power required by the transponder. This is where the higher part of the power which goes. But there are other devices or other circuits which are drawing the power, that is by the receive, the power by the receiver, power by the bus system. So, all together is the total power required by the satellite. Now, this what we described is a simple conversion of the frequency, is called bent pipe or transparent transponder, but in some cases more complex transponders are used, which is having onboard switching capacity. We will start discussion on this in the next class. Okay, right. Thank you very much.